Okay, here we are. We're going to look at photoelectric effect from a graphing perspective. If we manipulate the light, if we increase the frequency of the light, then what we're going to see is the kinetic energy of the ejected electrons increase. And if the intensity of the light increases, the incident light, the one that's being shown on the plate, then the number of electrons emitted will increase. And that we can measure with a multimeter. So if we were to go back to our diagram that we saw, the photomultiplier tube with the plates in it, and then it was attached to a multimeter. If we increase the intensity, the number of electrons would be emitted. If we increase the frequency, if we got over that threshold frequency, then the kinetic energy of the electrons increases. And we can see this graphically. So if we're looking at the kinetic energy of electrons versus the intensity of the incident light, what we see here is a graph that looks like this. So this is intensity of the initial light being shone on the plate, and here's the kinetic energy of the electrons. And what we see is if the intensity is bright enough, we'll see this. As it's increasing, as the intensity is increasing, the kinetic energy is maintained. The frequency of the light has to be greater than the threshold frequency. If we're looking at intensity versus the kinetic energy of the electron, where the light is less than the threshold frequency, we won't see those electrons come up off the plate. Okay, so it has to be greater than the threshold frequency for us to see the electrons move. When we look at the current versus wavelength, so here's the wavelength in meters, and here's current. What we see is at a certain point we're going to hit, as the wavelength increases, we're going to see the current to a maximum point. And after that, the current won't be affected anymore. Okay? But it says for some things we need to do a little bit deeper investigation. So if we look here, in a photoelectric experiment, maximum kinetic energy of the emitted electrons was measured based on the frequency of light hitting a metal surface. Data was collected and compiled into a graph as shown below. So there's data already given to us. So this is what we're looking at here on a graph like this. So here's 0, and then if you go 2 squares, you're going to be 0.5, 2 squares, 1.0, 1.5, 2, and 2.5. And this is going to be kinetic energy. Oops, we don't write kinetic energy that way. We write it this way. Kinetic energy of photoelectrons in electron volts is our units here on this scale. Here we would have 2 squares minus 0.5 minus 1.0 minus 1.5. And then across every square we'll give it 1. And so on. This is going to be the frequency of incident light. And this is times 10 to the 14. This is 1,4 right here. Okay? And so with the data collected, we know that there's a point here. Oh, I didn't extend my chart far enough. Roughly here. Okay, there's a point here at 3.5 and 0.7. We'll call that there. So this is 3.5 times 10 to the 14 hertz and negative 0.70 electron volts. This is point A. And then point B, we are going to put it at 9 and 1.6. So roughly right about there. And 1.6 electron volts. Okay, this is going to be point B. And so then when we draw a line from point A to point B, of course, you're going to use a ruler and it's going to look much prettier than that. Okay, right here we have the y-intercept, and it's negative 2.20 electron volts. And then what we can figure out is we can figure out slope. So if you're wondering where this data came from, it's just data that was collected. Okay, and what they got from an experiment. So slope equals rise over run. So negative 0.70 electron volts minus 1.6 electron volts over 3.5 times 10 to the 14 minus 9.0 hertz. And we end up with a slope value 4.18 times 10 to the negative 15 electron volts seconds. Okay? And so what are we looking at here when we have y is equal to EK and x is equal to threshold frequency? What we're looking at for slope is going to be equal to Planck's constant. Okay, and we know that Planck's constant is actually 4.14 times 10 to the negative 15. So when we use linear regression, when we use the line slope, slope line formula, y equals mx plus b, what pieces of information do we have? Well, let's look at our formulas that we have. We know that the energy in is equal to the energy out. We know that we have E of the incident is equal to work plus E of the kinetic energy of the electron. We know that when we isolate for kinetic energy, it's equal to work minus the incident energy. Sorry, I got that backwards. And we know that work, or this E kinetic energy is equal to Planck's constant times the threshold, or not the threshold, but times the frequency minus work. So when we look at this and we compare it to y equals mx plus b, we know that this from our graph is y. We know that this is our x. We know that this is going to be our y-intercept. And so then slope must be okay, so that's our slope line formula. Y being EKE, slope being Planck's constant, x being the frequency that was plotted, and the y-intercept, the negative 2.20 electron volts, being the work. So slope is going to be equal to your, to answer A, slope is equal to h. The significance or meaning of the y-intercept is negative work, and the significance meaning of the x-intercept is that we can actually figure it out. Sorry. So the x-intercept, when we go back on our graph here, we can see that it crosses this is the x-intercept. Okay? So where it's crossing the x-intercept, that in itself is our threshold frequency. That's the minimum amount of frequency required to eject the electrons off the plate. So when we use our graph to determine our work function of the metal, we look at, from our formula up here, negative W is equal to the B, or the y-intercept, and where it crossed the line was negative 0.20 electron volts. Okay? We don't worry about the sign when we're talking about work, or we could say this, negative work is equal to negative 2.20, so work is equal to 2.0 electron volts.